Hello, I am Mariam Hussainy. I'm gonna be presenting our research that discusses a computational approach for optimizing the daylighting performance of existing buildings. We noticed that many buildings in Egypt ignore their climatic conditions by extend the use of glaze, which causes glare and increase the cooling loads. While using artificial light sources in offices can account for as much as 50% or even more in deep plan buildings. Where deep plan buildings are buildings with floor plan greater than 10 meters depth, which have been a common practice in office buildings designed for economic reasons. So the deep core areas of these buildings cannot be naturally illuminated by side windows and depend entirely on electricity for illumination. Therefore, the stark contrast between the bright windows and the dark rear can also create discomfort glare, so as a result, occupants tend to pull down the curtains and switch on electric lighting. While based on a previous research, office workers with more light exposure at the workplace have better quality of life compared to office workers with less light exposure. The motivation behind this research was the problems caused by the lack of lighting, which are that depression, visual discomfort for occupants, and increase in the electricity consumption. So the objective of this research is to provide a workflow to assess and optimize daylighting performance in buildings, utilizing simulation techniques for identifying the most efficient daylight performance by incorporating parametric optimization tools to enhance the daylighting performance of existing buildings. So the workflow is going to be examined over an office building located in New Cairo, Egypt. The results shall determine whether the daylight provision is sufficient or not. And the study will show how these problems can be approached using different optimization techniques to enhance the daylighting quality and quantity. So the workflow starts by modeling the original building with the surrounding context. This is followed by daylighting simulation of the original building to examine the daylighting performance, and then to enhance the daylighting quantity of this building using material modifications, and finally enhance the daylight quality of this building using shading devices like louvers and vertical screens. So regarding the site analysis, the building is located in New Cairo, Egypt, directly on the Southern Street Road, and the building was selected because it represents a typical type of these office buildings with a high glazing percentage. Starting with modeling the original building with the surrounding context, the building is modeled with the outer skin and the window-wall ratios. And then the daylighting simulation of the original building results showed that the building suffers from lack of lighting, as the SDA percentage reached only 27%, while the glare percentage reached 40%. So this means that the building suffers from lack of lighting and glare beside the windows. So based on previous recommendations from previous researches, the deep core areas of these buildings cannot be illuminated by side windows and depend on artificial lighting. Also, the high reflective ceilings had the ability to better bounce the daylight around the space and reduce the extreme brightness. And finally, the WBDG recommends keeping the ceiling reflectance over 85%, walls over 50%, and floors around 20%. So therefore, to enhance the daylight quantity, the material modification step included replacing regular gypsum board ceiling with high reflective ceiling, and change the wall material to white glossy paint with 60% reflectance, and to add a curtain wall to the inner western facade with a window-wall ratio of 75%. So the results showed that the SDA percentage increased from 27 to 87%, which solves the issue of insufficient lighting. However, the increase in daylight caused an increase of glare from 40 to 60%. Therefore, to optimize the daylight quality, it was recommended to use shading system. So the first examined shading system is louvers with a parametric count, tilt, angle, depth, and rotation. The second shading system is a vertical screen with a parametric tilt, angle, and scale. So the results of the louver system showed that over here, a case A achieved the highest SDA percentage of 77%. However, the accompanying glare reached 31%. Therefore, the utilization of the louvers has the potential to enhance the daylight. However, it did not achieve the compromise between the sufficient daylight and minimum glare. So the second shading system, which is the vertical screen, achieved much better results with an SDA percentage of 78% and overlet percentage as low as 14%. In conclusion, the study proves that improvements in daylight performance can be achieved using the right methodology, and the workflow has the ability to control many design parameters for each type of building. Although the assessment of an optimization is preferably to be done in the early design stage, however, the paper proved that retrofitting measures could still enhance the daylight performance. While the workflow can be generalized in any type of building after evaluating the performance and tailoring the parameters according to each condition.